Hey everybody, welcome to your first video on Taylor series. So we did several days of in-class notes introducing sequences, series, geometric series. We talked about power series. I want to do a really quick recap of what we did in class because this is brand new material. It's good to see it more than once so it doesn't fly over your head and jumble up into a bunch of confusion. So in class so far, we did geometric series, like I said. We started with our first Taylor series that you're going to have memorized for the exam, which is f of x is 1 over 1 minus x. We found the power series. We did long division, remember. We found the interval of convergence. And this is a polynomial here, and it's a polynomial approximation. And we're going to use this polynomial to approximate actual function values. Then we used this polynomial, which is actually a geometric series. In this case, it's more specifically a power series. We use it as a building block to get new power series. And in class, we found these five, right here. We found these five. So what we did with the ones that I have in pink here is we compare these directly to 1 over 1 minus x because they were almost 1 over 1 minus x with just something substituted in for x and something's replaced, or we replaced 1 with something to get a new a sub 1 term. And we manipulated to get the interval of convergence as well. What we did with the things in green is we compared them not directly to 1 over 1 minus x, but we saw how this was a integral and this one was a derivative. So for this one, we did the integral of 1 plus x squared plus x cubed, and here we did the derivative of our original 1 plus x squared plus x cubed. The derivative of all these terms were our new power series. Notice for these, when you do derivatives and integrals of your building blocks, which originally had an interval of convergence of 1, when you do derivative and integral of this guy, the interval of convergence comes with it. So we didn't have to manipulate it. It was just the same exact thing. So I want to show you a visual of each of these. Here's the original 1 over 1 minus x. This original guy had an interval of convergence from -1 to 1. We truncated it for this case when I did it at the third degree polynomial. Our first variation was 2 over 1 minus x cubed. You can see in pink I have my original, in blue is my approximation. This one had an interval of convergence -1 to 1. And if you look on the graph from -1 over to 1, it's doing a good job. The next variation that I had was this one, x over 1 minus 2x squared. Here's my polynomial approximation in blue. This one had an interval of convergence -half to half. So if you go down and up, -half and half, you can see it's doing a good job there. Does a horrible job for anything way to the left and to the right. It's not even going close to that. Our next one, our third one, this one had an interval of convergence -1/2 to half whenever we manipulated it. This was 3 over 1 plus 2x. So you can see that it has a smaller interval of convergence. And here we have the integral one. So this one is a really interesting original curve. Check this one out. My original function was negative natural log of absolute value of 1 minus x. And my polynomial can only do part of the graph because no polynomial goes up and back down again. So it's doing a good job from -1 to 1 here. This is a scale of 1 is each box. And the last one we did is this one here. In pink is my original 1 over 1 minus x squared. That's rational. And here's my approximation based off of the original f of x, and it had an interval of convergence -1 to 1 again. So as you can see, all this work we've been doing is just to approximate any function with a polynomial at a certain area, a certain interval of convergence. So let's go back and get some new stuff in. So everything I have written, now this stuff you already had, so you don't have to rewrite this, but this stuff is going to be new. In class, we left off with the question, what if we have functions that aren't rational? So we've been manipulating things that were based off of 1 over 1 minus x, but not everything can be manipulated from this, and not everything's a derivative or an integral of this. There's all kinds of functions. Let's take a look at the second major series you're going to have to know, and it's e to the x. So what we're going to do is try and find a higher order polynomial for this one. Now we already did it for 1 over 1 minus x. It was this. We want to find one for e to the x, and we're actually going to create it. We're not going to do long division. For this one, we did long division. This one, we're actually going to take higher order derivatives over and over again. Now, we already know how to do an approximation for this using a tangent line. Let's take a look at how a tangent line works again. Find a tangent line for this and then build off of it. So a tangent line, the way it works is we need a point and a slope. Let's make it real general right now for any function, not just e to the x. If I want to approximate f of x, a point would be some a value. The y value would be f of a. The slope would be f prime of a. So I have a point and a slope, very general here. So y minus y1 equals m x minus x1. If I solve for y, then it's f of a plus f prime of a x minus a. This is actually a first-degree Taylor polynomial. I mentioned in class before that tangent lines really are Taylor polynomials to the first degree, but when it's written like this, it's really going to start looking like a Taylor polynomial. We'll see more and more things that look like this. Now let's make it a little more specific for e here. So our goal is to extend this derivative business to higher order derivatives. And we're going to get all the information we need. Now, I'm going to introduce the idea right now of a centering point. A centering point is going to be real important when you write series. We haven't really talked about it yet. We've just assumed the centering point is 0. And the easier ones do have a centering point of 0. When you say a series is centered somewhere, that just means where the tangent line is. So if I have some function like that, and it's centered at 0, like x is 0, that just means your tangent line would lie at 0. It wouldn't be somewhere else like over here, or over there. It's centered at 0. You can center your series anywhere. Wherever you center it will just be where your first derivative, your tangent line is. We're going to start, like I said, at 0 for all of these, and then we'll start messing around with centering them somewhere else. So let's take f of x and let's center it at 0. So what we have here is, let's get a point and a slope. We're still just talking about tangent lines for just another second here. If I want to write a tangent line for e to the x, because remember we're focusing on e to the x for the first half of this video at least, I need a point and a slope. So a point, when x is 0, I need a y value. F of 0 is 1. So that means my ordered pair is 0, 1. My slope, f prime of x, is just e to the x. So that means f prime of 0 is e to the 0, which is 1. So I have y minus y1 equals m x minus x1. When I plug into there and I solve for y, I get y equals 1 plus 1 times x minus 0, or this. So again, that's my tangent line. I could approximate e to the x with a tangent line around 0, but I want to do even better. We want a higher power. I actually want to start with finding a second degree approximation. So this is our first degree approximation, tangent line. Let's get a second degree. Let's truncate our infinite polynomial to the second power. And polynomials in general have the form c0 plus c1 plus c2. Now we're going to start getting into some heavy notation here. These are your coefficients. Every polynomial in front of the variables like x, x squared, x cubed, you have coefficients. The way to make a Taylor series is you have to find out what these coefficients are. Now notice whenever we did this guy, all the coefficients were 1, which makes it kind of easy to find. There is not any other Taylor series that has all the coefficients of 1. So our main goal when we do this is to find the coefficients, and that's what helps us make our Taylor series. And when you write this out, notice that your subscripts, which are these guys down here, match the power of your variable. This is really x to the first. This technically is x to the 0 afterwards. So if I want to write p sub 2, which is a polynomial to the second degree, we need all the coefficients of p sub 2. So let's write out our second degree polynomial, truncate it. It's not plus dot 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 anymore. I truncated it already. So p sub 2 of x will be c0 plus c1x plus c2x squared. What we're going to do here is compare our actual function to our polynomial. First, just original. Then we're going to compare the derivative of each. Then we're going to compare the second derivative of each. So what you do when you do this is you say, all right, p of x is this, f of x is this. Evaluate them each at the centering point. F of 0 is easy. E to the 0 is 1. If I evaluate my polynomial at 0, this will zero out, that'll zero out. I'm left with c sub 0. Now you have to remember, this polynomial is supposed to approximate e to the x. So our polynomial values should be the same as our function values, around 0, in order for it to do a good job. So what we're going to do is set our polynomial value equal to our function value. Our polynomial value is c naught. Our function value is 1. Well, this one's easy. It just says our first coefficient here is 1. So again, the function values need to be the same at x equals 0, so we're going to set them equal to each other. Okay, so that got us the first coefficient. Let's get more. To get the next coefficient, c sub 1, we're going to take the derivative of p. Well, the derivative of this, derivative of c naught, that's a constant, is 0. Derivative of c1x is c1. Derivative of c2x squared is 2c2x. The derivative of f is just e to the x. Evaluate both first derivatives at 0. So what I'm going to do now is say, okay, take p sub 2 prime of 0. If I evaluate this at 0, it's going to be 0. C sub 1, there's no x, so you can't really plug anything in. So evaluate at 0, the polynomial c1. Evaluate the function derivative at 0, you get 1. Set this equal to this, meaning set this equal to this. So c1 is 0. I'm sorry, c1 is 1. So now I have this guy. So we set our functions values equal to the polynomial value after each derivative. So we're building polynomials by taking successive derivatives. All right, so we're going to do a second derivative now. Moving on up, so I'm going to do p double prime of x. So that means I'm going to do the derivative of this. Well, the derivative of a constant is 0, so that's why I don't have c1 anymore. Derivative of t c sub 2x is, or I'm sorry, 2c sub 2x is 2c sub 2. The derivative of f prime, which is the second derivative, is e to the x again. This one's easy because e to the x is always e to the x, and it's always 1 at 0. So now I'm going to set my polynomial value equal to my function value, meaning I set 2c sub 2 equal to 1. Solve for c2, c sub 2 is 1/2. Whew, all right, we got it. So what this means is p sub 2, which started as this. This is general. I have no idea what my coefficients are. Well, I just took more and more derivatives, and I found all my coefficients. So c sub 1 was 1. I'm sorry, c sub 0 was 1. C sub 1 was 1. C sub 2 was 1/2. The x's come with it. So by finding my coefficients, I was able to find a series. This is a power series. More specifically, we're going to call it a Taylor series in just a moment. Notice that hiding in here, well, it's not really hiding, it's right in front of you. Within my second degree approximation is my first degree approximation, which was the tangent line. So you could have done this in October or September. Now we're building off of it. And let's graph to see how good of a job, like if I truncate this at x squared, is this even doing somewhat of a good job? Let's see. Let's go to Desmos. Come on, buddy. Where are we? So here's e to the x. If I only go to the second degree, which seems like it wouldn't be that accurate, it's doing a pretty good job. Remember, we centered at 0. So if I zoom in on x equals 0, it's doing a really good job. And if I zoom in enough, you can't even tell them apart. If you zoom out, you can see that it does a really bad job if you go to negative infinity. The more and more terms you add to this polynomial, the closer and closer your approximation will be to the curve. I'm going to end this video here. In the next video, we're going to do e to the x again, but p sub 4, so we're going to get higher powers, and we're going to write a rule for the general term. I'll also do cosine, and hopefully I'll fit both of those in the next video.